In a three-phase four-wire electrical system, the method for calculating voltage drop depends on the type of load being supplied. For single-phase loads connected between a phase and the neutral conductor, the voltage drop calculation utilizes the phase-to-neutral voltage. Conversely, for three-phase loads connected across all three phases, the calculation employs the phase-to-phase voltage. Firstly, considering single-phase loads, the voltage drop is determined by the formula voltage drop equals phase-to-neutral voltage multiplied by the current multiplied by the impedance. In this formula, voltage drop is expressed in volts, the phase-to-neutral voltage is also in volts, the current is in amps, and the impedance of the feeder is in ohms. Secondly, for three-phase loads, the voltage drop is calculated using a similar formula, but substituting the phase-to-neutral voltage with the phase-to-phase voltage. The formula becomes voltage drop equals phase-to-phase voltage multiplied by the current multiplied by the impedance. Again, voltage drop is in volts, the phase-to-phase voltage is in volts, the current is in amps, and the impedance is in ohms. It is crucial to accurately determine the impedance of the feeder conductors. This impedance value should correspond to the appropriate configuration, whether it's line-to-line or line-to-neutral, depending on the specific load type being analyzed. Using the correct voltage, either phase-to-neutral or phase-to-phase, along with the accurate impedance is essential for achieving a correct voltage drop calculation. The magnitude of the current also affects the amount of voltage drop. Higher current will cause a larger voltage drop across the feeder. This underscores the importance of proper conductor sizing to minimize impedance and maintain voltage levels within acceptable limits. In summary, the key distinction in voltage drop calculations for three-phase four-wire systems lies in recognizing the load type. Single-phase loads necessitate the use of phase-to-neutral voltage, while three-phase loads require the phase-to-phase voltage. Always ensure that the impedance value used in the calculation corresponds to the appropriate wiring configuration. Correct application of these principles is essential for ensuring optimal performance and reliability in three-phase four-wire electrical distribution systems. Understanding voltage drop and its calculation are important for a variety of reasons. Firstly, maintaining adequate voltage levels at the point of utilization is crucial for the proper operation of electrical equipment. Excessive voltage drop can lead to reduced performance, overheating, and even premature failure of equipment. Secondly, voltage drop affects the efficiency of the electrical system. When voltage drops occur, power is dissipated as heat in the conductors, resulting in energy losses and increased operating costs. Thirdly, electrical codes and standards often specify maximum allowable voltage drop limits for branch circuits and feeders. Compliance with these limits is necessary to ensure safety and prevent hazards such as fire and electric shock. To minimize voltage drop, several strategies can be employed. Firstly, using larger conductors with lower resistance can reduce the impedance of the circuit. Secondly, shortening the length of the circuit can also decrease impedance and voltage drop. Thirdly, minimizing the load current by using energy-efficient equipment can help reduce the overall voltage drop. Fourthly, properly balancing the loads across the phases in a three-phase system can minimize neutral current and voltage drop. When calculating voltage drop, it is important to consider all factors that contribute to impedance, including conductor material, size, length, temperature, and installation method. Tables and formulas are available in electrical codes and engineering handbooks to assist with these calculations. Accurate voltage drop calculations are essential for ensuring the safe, efficient, and reliable operation of electrical systems. By understanding the principles of voltage drop and implementing appropriate mitigation strategies, electrical professionals can design and install systems that meet the needs of their customers while complying with applicable codes and standards. The phase-to-neutral voltage is the voltage measured between one of the phase conductors and the neutral conductor in the system. The phase-to-phase voltage is the voltage measured between any two of the phase conductors. In a balanced three-phase system, the phase-to-phase voltage is equal to the square root of 3, which is approximately 1.732 times the phase-to-neutral voltage. For example, in a 208/120 volts three-phase system, the phase-to-neutral voltage is 120 volts, and the phase-to-phase voltage is 208 volts. It is important to note that the voltage drop calculation methods described above assume a balanced three-phase system. In an unbalanced system, where the loads on each phase are not equal, the voltage drop calculation becomes more complex and may require the use of specialized software or hand calculations. In addition to the formulas provided earlier, there are other methods for calculating voltage drop, such as the use of voltage drop tables and software tools. Voltage drop tables provide pre-calculated voltage drop values for various conductor sizes, lengths, and current levels. These tables can be a convenient way to quickly estimate voltage drop in simple circuits. Software tools can provide more accurate voltage drop calculations for complex circuits with multiple loads, conductor types, and installation conditions. These tools often incorporate advanced features such as load flow analysis and harmonic analysis to provide a comprehensive assessment of voltage drop and other electrical parameters. When performing voltage drop calculations, it is important to consider the ambient temperature and conductor temperature rating. The resistance of a conductor increases with temperature, which can affect the voltage drop. Electrical codes specify maximum allowable conductor temperatures for different insulation types. It is also important to consider the dirting factors for conductors installed in conduit or cable trays, as these factors can reduce the ampacity of the conductors and increase the voltage drop. In addition to minimizing voltage drop in the feeder and branch circuits, it is also important to ensure that the voltage at the service entrance is within acceptable limits. Utility companies typically provide voltage regulation to maintain voltage levels within a specified range. However, voltage fluctuations can occur due to changes in the utility grid or the operation of large loads. Voltage spikes and swells can cause equipment malfunction and damage, so it is important to monitor the service entrance voltage and take corrective action if necessary. Voltage drop calculations are an essential part of electrical system design and analysis. By understanding the principles of voltage drop and using appropriate calculation methods, electrical professionals can ensure that electrical systems operate safely, efficiently, and reliably. The National Electrical Code, or NEC, provides guidelines and regulations for voltage drop in electrical systems. It's important to consult the latest edition of the NEC for specific requirements in your area. While the NEC does not mandate specific voltage drop limits for all installations, it recommends that voltage drop on branch circuits should not exceed 3% and the combined voltage drop on feeders and branch circuits should not exceed 5%. These recommendations are intended to ensure that electrical equipment receives adequate voltage for proper operation and to prevent excessive energy losses. The NEC provides tables and formulas for calculating voltage drop, taking into account factors such as conductor size, length, current, and power factor. It also specifies requirements for conductor ampacity, which is the maximum current that a conductor can carry without exceeding its temperature rating. Proper conductor sizing is essential for minimizing voltage drop and ensuring that conductors can safely handle the expected load current. In addition to voltage drop calculations, the NEC also addresses other aspects of electrical system design such as overcurrent protection, grounding, and wiring methods. Compliance with the NEC is essential for ensuring the safety of electrical installations and preventing hazards such as fire and electric shock. It is important to note that the NEC is a minimum standard and local jurisdictions may have additional requirements that must be met. Electrical professionals should be familiar with the NEC and any applicable local codes and regulations. When designing and installing electrical systems, it is important to consider not only the NEC requirements but also the specific needs of the application. Factors such as the type of equipment being served, the expected load current, and the distance from the power source should be taken into account. A well-designed electrical system will provide adequate voltage, minimize energy losses, and ensure the safe and reliable operation of electrical equipment. Voltage drop calculations are a fundamental aspect of electrical engineering and are essential for ensuring the proper functioning and safety of electrical systems. By carefully considering the factors that influence voltage drop and using appropriate calculation methods, electrical professionals can design and install systems that meet the needs of their customers while complying with applicable codes and standards. Understanding the concepts and calculations related to voltage drop is also crucial for troubleshooting electrical problems. Excessive voltage drop can be a symptom of various issues such as undersized conductors, loose connections, or overloaded circuits. By measuring voltage drop and comparing it to calculated values, electricians can identify the source of the problem and take corrective action. In addition to the traditional methods of calculating voltage drop, there are also software tools and online calculators that can simplify the process. These tools can automate the calculations and provide more accurate results, especially for complex circuits with multiple loads and conductor types. However, it is important to understand the underlying principles of voltage drop and to verify the results obtained from these tools. Voltage drop can also be affected by harmonics in the electrical system. Harmonics are non-sinusoidal waveforms that can be generated by electronic devices such as computers, variable frequency drives, and LED lighting. Harmonics can increase the current flowing in the conductors and can also cause additional voltage drop. In some cases, it may be necessary to install harmonic filters to reduce the levels of harmonics and mitigate their effects on voltage drop. In addition to the factors mentioned earlier, the power factor of the load can also affect voltage drop. Power factor is a measure of how effectively the electrical power is being used. A low power factor can increase the current flowing in the conductors and can also increase the voltage drop. Power factor correction capacitors can be installed to improve the power factor and reduce voltage drop. Voltage drop is an important consideration not only in electrical power systems but also in other applications such as electronic circuits and telecommunications systems. In these applications, voltage drop can affect the performance of electronic components and the quality of signal transmission. Similar principles and calculation methods can be applied to analyze voltage drop in these systems. In conclusion, voltage drop is a critical parameter that must be considered in the design, installation, and operation of electrical systems. By understanding the factors that influence voltage drop and using appropriate calculation methods, electrical professionals can ensure that electrical systems operate safely, efficiently, and reliably.